Good morning, everyone. I am Rajni Markham, a postdoc at Artificial Intelligence and Robotics Laboratory, Indian Institute of Science, Bangalore, headed by Professor Suresh Sundaram. I'm working on controls, navigation, and system identification for AUVs. Recently, I'm also looking into underwater image analysis. Today, I'll be presenting our work on data-driven coefficient estimation for autonomous underwater vehicle depth subsystem. I'm grateful to IEEE SMC for accepting our work and giving us a platform to present it. Let's begin. The presentation is organized as follows. We begin with the introduction to AUVs and establish the motivation for parameter identification. Next, we will investigate the relevant literature in the field before going into methods where we describe physics-informed neural networks and sparse identification of nonlinear dynamics. Then we describe the input signals and performance measures used in the study. We then glance at the results and conclude the presentation with a few key points and directions for future research. Autonomous underwater vehicles, or in short, AUVs, have revolutionized ocean exploration. Their ability to perform tasks such as underwater mapping, monitoring, and various operational duties is invaluable. However, accurate dynamic modeling is critical to their successful deployment, particularly in harsh, deep sea environments. To enhance their design and control, understanding the hydrodynamics of these vehicles are essential. That's where system identification comes into play by helping us develop accurate models based on real world data. Hydrodynamic coefficients are crucial for precise maneuvering of AUVs. Combining traditional methods like computational fluid dynamics with data driven techniques can significantly improve our ability to estimate these coefficients. Several techniques have been explored in the literature for parameter identification. A few notable works include the optimized unscented Kalman filter, which utilizes gradient descent for recursive tuning but suffers from overparameterization. Another technique using long short term memory, LSTM neural networks, but these require a large amount of training data. More recently, a physics informed identification method was proposed using sequential thresholded least squares along with Bayesian optimization. However, these works focus on specific subsystems like raw subsystem, leaving gaps in other areas like depth control. That is why this work focuses on system identification, especially in depth subsystem of AUVs with limited and noisy training data. In this work, we focus on the depth subsystem of AUVs. The primary variables of interest include pitch angle, depth, speed, and pitch rate. While some of these variables are known, others need to be determined through system identification. For example, moment of inertia is known to us, added mass is known to us. However, the coefficients like mq, m theta, and m delta are unknown. The governing equations of depth subsystem are presented in both differential, which is a second order linear one, and state space forms, laying the foundation for the methods we use to identify unknown parameters. Physics-informed neural networks have been widely used in simulating physical systems and also in inverse problems for determining unknown parameters in dynamics. Physics-informed neural networks, in short PINs, have gained popularity in the above fields as they can reliably emulate the dynamics of the system in the presence of limited experimental data by incorporating the governing equations of the system into learning. Hydrodynamic coefficient determination in AUV dynamics is an inverse problem. PIN architecture shown here in this figure is used for this problem. It has one input, the time, followed by a few hidden layers, and an output layer with one neuron that predicts the state variable theta. The loss function for PIN here has three components: the ODE part, the initial condition part, and the data part. The ODE part of the loss function enforces the AUV physics into the function approximation. It is the residual of ODE itself. The initial condition part of the loss function imposes the initial conditions on PIN output. We assume zero initial conditions for simplicity. Finally, as this is an inverse problem, data plays an important role in parameter determination. Hence, an additional mean squared error term is added to the loss function to account for the available sensor data. The overall loss function is the sum of these individual components. The pin parameters and the unknown dynamics coefficients are jointly optimized through gradient descent. In another formulation, we use the theory of functional connections, in short TFC, to incorporate the initial condition directly into the pin output. In this formulation, only the ODE and the data parts of the loss functions are used for pin optimization. Pin falls into both parametric and non-parametric methods for system identification. Sparse identification of nonlinear dynamics, SINDI, is a data-driven optimization technique to extract the dominant dynamics from noisy measurement data. SINDI formulates the relationship between the state vector and its derivative using regularized linear regression. A library of candidate functions of the state variable psi is designed beforehand using existing knowledge of the system. The time derivative of the state variable is then expressed as a linear combination of these candidate functions through coefficients zeta. The hydrodynamic coefficients determination problem uses the AUV dynamics model, which contains the control signal, the Stern angle. The candidate function library psi is modified by including a few columns containing the Stern angle. The loss function for SINDI includes the mean square error between the time derivative of the state variables and its linear approximation. Additionally, it contains an L2 regularization term on coefficient vector. The regularization ensures that the recovered coefficients are sparse, and as a result, only the dominant candidate functions survive in the final approximation of the AUV dynamics. The hyperparameter lambda is set to 0.05 and loss function is optimized using the sequential thresholded least squares algorithm. In the AUV dynamics, the Stern angle represents the input signal. This signal is designed to excite all the modes in the system so that parameters can be identified accurately. We chose two profiles, the multi-step and the sinusoidal. The multi-step profile is a combination of step functions. For the first 5.5 seconds, the Stern angle is 0. For the next 3 seconds, it is held at plus 3 degrees. For the next 2 seconds, it is held at minus 2 degrees. Then it is kept at 2 degrees for the next 2 seconds. Finally, the Stern angle is kept at minus 1 and 1 degree respectively for 1 second each, and then it is taken back to 0 again. The multi-step profile is smoothened with a low-pass filter before simulations. The sinusoidal profile is a combination of two sinusoids with different frequencies. In the plot, the Stern angle values are in degrees. The input profiles are of 10 seconds duration. Three metrics are used to assess the performance of the proposed methods. The percentage error in the coefficients is used to check the accuracy of the coefficient estimation. The convergence of the resulting state variables is checked using mean absolute error and the mean squared error metrics. Two setups are used to assess the performance, noiseless and the noisy case. In the noiseless scenario, the simulated states are directly used for parametric estimation, whereas in the noisy scenario, a random Gaussian noise is added to the simulated states before using them for coefficient determination. Looking at the results in the noiseless case, SINDI outperformed all the other methods across both input profiles, showing improvements of several orders of magnitude in percentage error, MAE and MSE. This demonstrates that SINDI is well suited for systems where noise is not a significant factor and the data is relatively clean. Now, when Gaussian noise is added, we see a shift in performance. PIN combined with temporal Fourier continuation performs better on the multi-step input, achieving a 6 to 8% improvement over SINDI. On the other hand, SINDI still performs well on the sinusoidal input with improvements of 6 to 16% over PIN and PIN with TFC. Overall, while noise introduces challenges, both methods show competitive performance in capturing the AUV dynamics. And we see that in the table we have highlighted in multiple places. That shows that we can choose the estimated parameters from either PIN or from SIMD. Here we have the state variable plots for different input profiles. The input, which is a multi-step profile, is smoothened using a low-pass filter to account for noisy data. As you can see from the plots, all methods perform closely on the sinusoidal input, confirming the robustness of these techniques. To conclude, this work addresses hydrodynamic parameter identification in the depth subsystem of AUVs for the first time. We found that SIMD generally provides the best results in the noiseless condition, while PIN with TFC performs better under noisy multi-step inputs. Our future work includes extending this analysis to 3 DOF and 6 DOF nonlinear models of AUV dynamics and further optimizing these methods for real-world applications. Thank you for your kind attention. If you have any questions, I would be happy to answer them now.